Before I can even talk about black holes or quantum mechanics, I have to start with something way more basic, something ancient, invisible, and yet absolutely essential: measurement. Imagine a world before clocks, before mathematics, before even the idea of a second or a meter. How did people make sense of the world around them? To measure is to compare. This is longer than that, or this lasts longer than that. Early humans noticed the sun's shadow shifting as the day passed, so they stuck a stick in the ground and watched its shadow move. Behold, the sundial, not just an instrument, but humanity's very first scientific clock. It was simple, but it worked. The sun's position became our first reference for time. But what about when the sun was gone? The answer: water clocks, sand trickling in hourglasses, even burning candles. Anything that changed in a predictable way could become a tool for measurement. These weren't perfect, but das in Microstauer or Poststau, that are good enough to organize daily life, mark religious rituals, or send ships across the sea. Still, measuring time is only half the story. To measure anything, you need to set up rules. Enter the ruler and the compass, the ultimate duo of basic tools. The ruler, just a straight edge with regular marks, let us define length and distance. The compass, 2 arms and a hinge, let us draw circles, bisect lines, and bring geometry to life. With these, ancient scientists could compare, calculate, and build. Measurement is not just about numbers, it's about trust. If I say the shadow is 3 feet long, or this stick is 5 cubits, you and I need to agree on what a foot or a cubit actually is. That's why, over time, standards became critical. Fixed lengths and precise clocks, so everyone could speak the same quantitative language. Fast forward to the 20th century. We moved from ticking pendulums and swinging gears to something much, much smaller: atoms. The atomic clock uses the vibration of cesium atoms, billions of times per second, to define a second with incredible accuracy. It's so precise, if you ran one for millions of years, it wouldn't lose even a fraction of a second. So, from sundials to atomic clocks and from the humble ruler to the compass, measurement has been the steady heartbeat of science. Without it, observation is just opinion. With it, we build everything from skyscrapers to spaceships, and we trace the universe back to its very first moments. This is Foundation Instruments, a journey through the tools that made science possible. I invite you to subscribe to the For Science Sala Lotfi channel to keep exploring more science and knowledge.
Welcome to For Science Sala Lotfi channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Sala Lotfi channel، العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Before clocks and smartphones, humanity looked up for answers. The greatest clock wasn't built. It was the cosmos itself. The sun, our original timekeeper, marked the passage of days with its steady journey across the sky. Our ancestors noticed the sun's predictable rise and set, and realized this was more than a light show. It was a way to measure life. Imagine living thousands of years ago, with no hours or minutes, just light and darkness. But you're observant. You notice shadows change as the sun moves. A stick in the ground casts a long shadow in the morning, shortest at noon, then long again in the evening. This was nature's timepiece, the earth spinning, the sun's light painting time on the ground. This realization was a leap for humanity. We began to measure time, not just experience it. The sky became a giant clock face, the sun its single sweeping hand. This simple observation connected our daily lives to the grand motions of the solar system. We were learning to read the universe's first word, time. This first clock wasn't perfect, but it was a start. By observing the world, our ancestors harnessed a fundamental principle, a rotating planet orbiting a star. They brought the measurement of time down to Earth. The day could now be divided and tracked. The journey to understanding time began not with a tick, but with the silent movement of a shadow. The sun's path gave structure to our days and a sense of order to our lives. This cosmic clock was both universal and deeply personal. It was a partnership between human curiosity and celestial mechanics. The sun's movement was our first lesson in the language of the universe. With each sunrise and sunset, we grew more attuned to the rhythms of the cosmos. The measurement of time started with a glance at the sky. And so, humanity's quest to capture time began. How do you turn this cosmic observation into a tool? You build a sundial. At its heart is the gnomon, the part that casts the shadow. Think of it as the finger of the clock, but its shadow does the pointing. As the Earth spins, the sun's apparent motion moves the gnomon's shadow in a predictable arc. Watching a sundial is watching our planet turn. The shadow sweeps across a dial marked with hours, making time visible. Now, people could agree on the time of day. Let's meet when the shadow touches the third mark. The sundial brought a shared rhythm to communities. For accuracy, the gnomon's slanted edge must be parallel to Earth's axis, adjusted for your latitude. This clever design accounts for the sun's changing height through the seasons. The gnomon isn't just a stick, it's a piece of science, connecting your backyard to the planet's axis. The sundial transformed the abstract passage of time into something tangible and communal. The sundial is more than a shadow caster. It's a model of Earth's relationship with the sun. Its shadow's movement is governed by the laws of celestial mechanics. The Earth rotates at about 15 degrees per hour, and the sundial translates this into hour lines. These lines aren't evenly spaced. They bunch at noon, spread in the morning and evening. Designing them required knowledge of angles and trigonometry. Ancient astronomers mapped the heavens onto a dial, turning geometry into a tool for daily life. The sundial made Earth's rotation observable, long before rockets or satellites. It was a daily lesson in astronomy, demystifying the heavens. The sun's movement became a predictable, measurable phenomenon. The sundial marked a shift from experiencing the world to understanding it. It proved we could decode the rules of the cosmos with reason and geometry. For all its elegance, the sundial had limits. It only worked when the sun shone. Clouds or nightfall stopped the clock. In cloudy regions, the sundial was often useless. At night, timekeeping relied on water clocks or candles. The sundial's reign ended at sunset. Time slept with the sun. It also told apparent solar time, which varies because Earth's orbit is elliptical and its axis is tilted. Days aren't all the same length, so a sundial can be up to 16 minutes fast or slow compared to modern clocks. Each sundial showed local time. Noon in Rome wasn't noon in Athens. Every town lived in its own time zone, synchronized with its own sun. This wasn't a problem when travel was slow, but it shows how time was once a local phenomenon. The sundial's accuracy was bound to the whims of weather and geography. It was a reminder that our ability to measure time was still limited. Time, as we knew it, was a product of the natural world. The sundial's legacy is profound. It taught us that time could be observed, divided, and shared. Yet, it was always local, defined by the sun above your village. Your day's rhythm was shaped by your environment and the seasons. Timekeeping was organic, woven into nature's cycles. The sundial marks a stage when we could measure the universe, but not yet master it. We could read the cosmic clock, but only on the sun's schedule. The sundial is a monument to our relationship with the cosmos. For most of history, time was a shadow on the grass, a direct connection to the universe. The sundial didn't just tell time, it told us our place in the cosmos. Subscribe to the For Science Sala Lotfi channel to discover more fascinating science videos.
Part 2. The Water Clock. Time as Steady Flow. For millennia, humanity's sense of time was tethered to the heavens. The sun's arc across the sky, the moon's phases, the slow wheeling of the stars. These were our grand cosmic clocks. But what happened when the sun disappeared? When clouds obscured the sky, or when the world was plunged into the long hours of night? To free time from the sun, a new kind of clock was needed, one that operated on earthly principles. Humans turned to the most fundamental of elements, matter itself, in its most fluid and constant form. They turned to water. The result was the water clock, known to the ancient Greeks as the clepsydra, which translates poetically to water thief. This ingenious device measured the passage of time by observing the steady, controlled flow of water from one vessel to another. It was a profound invention, not just for its function, but for what it represented: The earliest known examples date back to the 16th century BCE in both Egypt and Babylonia. The oldest surviving water clock, found in the tomb of the pharaoh Amenhotep I, was a simple stone vessel, wider at the top than at the bottom, with a small hole near its base. As water dripped out, a series of marks on the inner wall indicated the passing hours. It was a simple outflow clock, elegant in its design, but it held the seed of a technological revolution. The engineering was straightforward, yet nuanced. In an outflow clock, time was read from the decreasing water level in the upper vessel. In an inflow clock, it was measured by the rising water level in a lower receiving vessel. The key to accuracy was controlling the flow rate. This depended on two critical factors: the size of the orifice, or the hole from which the water escaped, and the head, which is the height of the water column above that hole. A higher water level creates more pressure, forcing the water out faster. Early clockmakers quickly realized that in a simple cylindrical vessel, the flow would slow down as the water level dropped. To compensate, they ingeniously shaped their vessels with sloped sides, wider at the top and narrower at the bottom, to ensure a more constant drop in the water level. Calibrating these clocks was an art, requiring careful observation and the painstaking task of marking the hours on the inside of the bowl. With this newfound ability to measure time indoors and at night, the clepsydra became indispensable. In Athenian courts, it was used to limit the speaking time for litigants, ensuring fairness. The phrase, "his water has run out," became a common expression for a speaker whose time was up. Temple priests used water clocks to regulate nocturnal ceremonies and rituals. Military commanders relied on them to time the changing of the guard during the long, dark hours of the night watch. Astronomers, needing to record observations when the sun was down, found them essential. The Greeks and later the Romans, obsessed with mechanics and precision, took the water clock to incredible new heights. The great inventor Ctesibius of Alexandria, living in the 3rd century BCE, engineered a revolutionary improvement. He designed a system that maintained a constant water pressure, or head, by feeding the main timekeeping vessel from a larger reservoir. An overflow pipe siphoned off any excess, ensuring the water level in the timekeeping tank never changed. This created a truly steady flow, a massive leap in accuracy. But Ctesibius didn't stop there. He automated the display of time. In his inflow clocks, a float would rise with the water level. This float was connected to a rack, a straight bar with teeth, which engaged a pinion, a small gear. As the float rose, the rack turned the gear, which in turn moved a pointer across a calibrated scale. Some of his clocks were even more elaborate, featuring automata, figurines that would move, drop pebbles, or blow trumpets to mark the hour. This was the birth of feedback mechanisms and complex gear trains in timekeeping. However, for all its ingenuity, the water clock was not perfect. Scientific accuracy remained an elusive goal. The laws of hydrodynamics were not yet fully understood, and several variables could throw off the clock's delicate balance. The first was temperature. Water's viscosity, its thickness or resistance to flow, changes with temperature. On a cold night, water would flow more slowly than on a warm day, causing the clock to run slow. The second, as early clockmakers knew, was water pressure. Unless a sophisticated constant head device like Ctesibius's was used, the dropping water level in an outflow clock meant a continuous decrease in pressure, and thus, a slowing flow rate. And finally, there was the geometry of the vessel itself. Perfecting the precise parabolic curve needed to counteract the pressure drop was an immense mathematical and manufacturing challenge. Despite these limitations, the pursuit of a better water clock drove innovation for centuries. The legacy of the clepsydra is immense. It represented a critical conceptual shift. Time was no longer just observed in the heavens. It could be contained, controlled, and measured on a human scale. It could exist indoors, at night, separated from the sky. The use of floats, gears, and feedback systems in advanced water clocks directly paved the way for the development of the first mechanical clocks in medieval Europe. The very idea of time as a continuous, uninterrupted flow is a powerful metaphor we owe to these ancient devices. Despite its inaccuracies, the water clock introduced a revolutionary and enduring idea, one that would define the future of horology and science itself. Time is something that can be engineered. If you enjoyed this video, please subscribe to For Science Sala Lotfi channel for more mind-opening science.
Before clocks, humanity lived by nature's rhythm, sunrise, sunset, and the changing seasons. Sundials and water clocks marked hours, but time was local and flexible. There were no minutes or seconds, just rough divisions of the day. As society grew, we needed a new way to measure time, steady, reliable, and universal. The journey from sundials to seconds would change everything. The leap forward came with the mechanical clock in medieval Europe. No longer tied to sun or water, these machines used falling weights and gears to keep time. The gears translated the slow drop of a weight into the steady movement of hands on a dial. But the real breakthrough was the escapement, a device that released the gears in tiny, regular steps. This created the first true tick-tock, a heartbeat for the machine. Early escapements, like the Verge and Foliot, rocked back and forth, letting the gears advance bit by bit. For the first time, time could be measured in equal repeatable units. These clocks were huge, often installed in towers, striking bells to announce the hour. They weren't very accurate, gaining or losing minutes each day, but they changed everything. Now, towns could coordinate, and life could be scheduled. The mechanical clock made time visible, countable, and public. It was a revolution. Time was no longer just a story told by nature, but a rhythm created by human hands. The world began to move to the beat of the clock. This new, mechanical time would soon demand even greater precision. The quest for accuracy was just beginning. The next breakthrough would make timekeeping truly scientific. The age of precision was about to dawn. Mechanical clocks were a marvel, but they needed a steadier rhythm. Galileo noticed that a swinging pendulum kept a regular beat, no matter how wide the swing. This insight led Christian Huygens to invent the pendulum clock in the 1650s. The pendulum's swing regulated the gears, making clocks far more accurate. Suddenly, clocks could measure not just hours, but minutes and seconds. Huygens' clock was 100 times more precise than its predecessors. This leap in accuracy transformed clocks from public timekeepers into scientific instruments. Now, time could be measured, compared, and trusted. The pendulum clock gave science a new tool and a new metaphor for the universe. The steady swing of the pendulum echoed the order scientists saw in nature. With precision time, the world was ready for a new era of discovery. The clock was no longer just a machine, it was a key to understanding reality. The age of scientific time had arrived. Accurate clocks changed more than just daily life. They changed how we think about time itself. Time became universal, no longer tied to a single place or event. Clocks in distant cities could be synchronized, making shared schedules possible. This new, abstract time powered science, commerce, and global coordination. The idea of a clockwork universe took hold. The cosmos itself seemed to run on regular, predictable laws. Scientists began to search for the gears and escapements of nature. The clock became both a tool and a model for understanding reality. Time was now a straight line, divided into identical, repeatable units. The steady tick-tock of the clock became the soundtrack of the modern world. With precise clocks, science could finally measure motion and change. Galileo's experiments with rolling balls and falling objects became possible to time accurately. Scientists could now define speed, velocity, and acceleration using numbers, not just words. The clock turned vague observations into hard data. Experiments could be repeated, measured, and compared. the laboratory became a place of discovery, powered by the steady beat of the clock. Physics transformed from philosophy into a true experimental science. The ability to measure time made new laws of nature visible. The clock was the scientists' most powerful tool. It gave science its rhythm and its credibility. Isaac Newton's laws of motion and gravity described a universe that ran like a clock. His equations depended on precise measurements of time. Velocity, acceleration, and force all required it. Accurate clocks let scientists test Newton's predictions, from falling apples to orbiting planets. The pendulum clock even revealed that gravity varied across the Earth, confirming Newton's theories. Engineers used these laws to build bridges, machines, and the modern world. The clock was the bridge between theory and reality. Without it, Newton's physics would have remained abstract. With it, the world became predictable, measurable, and controllable. The age of machines and science was built on the foundation of timekeeping. The clock was the silent partner in every scientific triumph. The mechanical clock transformed time from a local story into a universal language. It gave science a steady pulse, making experiments repeatable and results reliable. The great theories of physics, velocity, acceleration, gravity, depend on precise time. From water clocks to pendulums, and now to atomic clocks, our quest for accuracy continues. Today, clocks synchronize the world, power GPS, and test the limits of physics. But the principle remains. To understand the universe, we must measure its rhythm. The revolution that began with the first tick-tock is still unfolding. Clocks gave us more than minutes and seconds. They gave us a new way to see reality. The heartbeat of science is the measurement of time. And with every tick, we discover a little more of the universe. If you enjoyed this journey through time, don't forget to subscribe to the For Science Salah Lotfi channel for more fascinating exploration.
For most of history, we measured time by watching things move. The sun, the moon, pendulums and gears. But all these methods rely on physical objects which are never perfectly reliable. Friction, temperature and gravity can throw them off. What if we could measure time using something more fundamental, something woven into the fabric of the universe? Enter the atomic clock. It doesn't tick like a normal clock. Instead, it listens to the rhythm of atoms. This leap is like going from a hand-drawn map to a satellite image. Atomic clocks don't just improve accuracy, they redefine what time is. They measure a property of nature that's the same everywhere, from Earth to distant galaxies. This new timekeeper forces us to rethink time itself, not as a human invention, but as a universal constant. It's a clock that measures the pulse of the cosmos. The atomic clock is our portal to understanding time on a truly universal scale. It's not just a better clock, it's a revolution in how we see reality. We're no longer bound by the limits of our own engineering. Now, we're listening to the universe itself. How do you build a clock out of an atom? You start with cesium-133, an atom with a perfectly stable rhythm. Inside, the electron and nucleus act like tiny magnets, flipping between two energy states. When you zap cesium atoms with microwaves at just the right frequency, they flip states. The atomic clock tunes its microwaves until it matches the atom's natural frequency. The atoms themselves tell the electronics what the correct frequency is. This creates a feedback loop, nature's own metronome. The result is a clock that counts time by the silent, invisible hum of atomic transitions. No gears, no ticking, just the pure rhythm of the universe. The cesium atom's song is one of the most stable beats ever discovered. It's nature's perfect pendulum. Once scientists locked onto the cesium atom's rhythm, they redefined the second. For centuries, a second was tied to Earth's rotation, a wobbly, slowing standard. In 1967, the world agreed. A second is now the time it takes for cesium-133 to oscillate 9,992, 631,170 times. This isn't a number we invented. It's a property of the universe. Every atomic clock on Earth is calibrated to this exact number. Now, a second is the same everywhere, on Earth, in orbit, or on another planet. This definition transcends geography and culture. By anchoring time to atomic vibrations, we found a standard immune to planetary quirks. The cesium atom's oscillations are unchanging. 1,000,000 years from now, they'll be the same. We stopped letting our planet tell us the time and started listening to the atoms themselves. It was a profound leap for science and humanity. Defining time by atoms broke our ancient link to Earth's cycles. Days, months, and years once came from planetary motion. The atomic clock shattered that perspective. Cesium's vibration is a quantum property, not tied to any planet or star. The atomic second is a universal unit, valid anywhere in the cosmos. This shift lets us measure time's strange behavior, like how gravity slows clocks. With atomic clocks, we can see Einstein's relativity in action. Time is not something we invented, it's a dimension we discovered. The atomic clock measures this dimension with clarity, revealing the universe's own heartbeat. We've learned to listen, gaining a deeper understanding of the cosmos. Atomic clocks are the invisible backbone of modern life. Without their precision, GPS, the internet, and global communications would fail. GPS satellites use atomic clocks to pinpoint your location. Just a microsecond's error throws you off by hundreds of meters. Telecommunications networks rely on atomic time to keep data flowing smoothly. Financial markets, phone calls, and streaming all depend on this global pulse. Scientists use atomic clocks to test relativity and synchronize telescopes across continents. Even geologists monitor volcanoes and tectonic plates with them. Atomic clocks aren't just timekeepers, they're essential scientific instruments. They keep our world running in perfect sync. Their silent precision powers the digital age. The journey from sundials to atomic clocks is really a journey in understanding reality. We once thought time was a human invention, a tool for order. The atomic clock shattered that illusion. Time is a physical property, a dimension woven into the fabric of the universe. The cesium atom's steady beat is a rhythm older than humanity. We didn't invent it, we discovered it. Now we read a cosmic clock built into the universe itself. The atomic clock gives us an objective measure of time, outside our own perceptions. It reveals time's complexity, how it bends with gravity and speed. More than a better clock, it's a window into the nature of reality. Time is out there, in every atom, a fundamental part of our cosmic journey. If you enjoyed this exploration, don't forget to subscribe to the For Science Sala Lotfi channel for more fascinating journeys into the universe.
Time alone is not enough to describe the universe. We often think of time as the great river that carries everything forward, but it's only part of the story. To truly capture the world around us, we need more than just the ticking of a clock. Sure, clocks let us track how things change, but to truly understand motion, I need distance. I need space that I can measure. Without a way to measure space, time is just an abstract idea. The universe is a dance of both time and space, and to see the full choreography, I need tools that let me measure both. Enter the ruler. It's so simple, a stick with marks. Yet it's one of humanity's oldest and most powerful inventions. Yet with it, space becomes something I can count, compare, and communicate. Suddenly, I can describe the world in numbers, not just words. Suddenly, the world isn't just out there. It's measurable, quantifiable, real. The ruler transforms the unknown into the known, the vague into the precise. But what if I want to explore more than just straight lines? What if I want to capture the curves and arcs that fill our world? That's where the compass comes in. With its sharp point and swinging arm, It opens up a new dimension of possibility. With a compass, I can draw perfect circles, bisect angles, and construct shapes no ruler alone could offer. Suddenly, geometry isn't just about lines. It's about the infinite variety of forms that can be created and explored. More than a tool for drawing, the compass lets me reason about space itself. It's a gateway to understanding symmetry, balance, and the hidden rules that govern shapes. With ruler and compass together, the world of geometry unfolds. Every construction, every proof, every elegant solution starts with these two. I can prove theorems, design buildings, and engineer bridges that actually stand the test of time. These tools are the bridge between imagination and reality, between an idea and a structure that stands tall. Think about it. Every modern marvel, from the pyramids to particle accelerators, is built on the foundation these tools created. The greatest achievements of civilization began with simple measurements and careful constructions. Geometry? Born from these two, the study of shapes, sizes, and the properties of space all began with the humble ruler and compass. Engineering? Impossible without precise measurements. Every bridge, every building, every machine relies on accuracy and repeatability. Architecture? It's all about turning lines and curves into reality. The ruler and compass are the artist's brush and chisel for the world of structures. And let's not forget experimental physics. Every experiment, every discovery, starts with careful measurement. Every measurement of speed, every calculation of force or energy, depends on two things: accurate length and accurate time. These are the pillars of every scientific investigation. Without them, there's no way to validate theories or uncover the laws of nature. Science would be nothing more than speculation, without the certainty that measurement brings. No kinematics, no mechanics, no real science, just guesswork. The ruler and compass are the difference between chaos and understanding. Rulers and compasses might look humble in a world of lasers and satellites, but they're the quiet heroes behind it all. Even the most advanced technology is built on the foundation they laid. They let us map the universe, test our ideas, and build the structures that shape our lives. They are the silent partners in every scientific breakthrough and every engineering triumph. So next time you pick up a ruler or snap open a compass, remember, you're holding the tools that built science. These are the instruments that turned curiosity into knowledge and knowledge into progress. The universe became measurable, and with that, understanding was finally within reach. With every line drawn and every distance measured, we move closer to unlocking the secrets of the cosmos. If you enjoyed this journey into the foundations of science, don't forget to subscribe to the For Science Sala Lotfi channel for more fascinating explorations. Join us as we continue to uncover the wonders of our universe.